certain mysteries of the universe have remained unsolved despite decades of research. Join us in delving into the answers to these questions. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These inquiries have captivated our minds for millennia. What if I told you that gravity is a lie, merely a construct of the human brain? This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. Let's delve into the nature of gravity and why time slows down to find out what on earth is wrong with gravity. We need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to address altogether. Newton's theory of gravity allows us to predict how things move under its influence, but doesn't explain why gravity exists or how it works. Newton knew this, of course. He essentially said that it's down to God. He believed that the most beautiful system of the sun, planets, and comets could only proceed under the dominion and counsel of an intelligent being. In other words, he provided the tools to calculate how objects move, but did not explain the underlying reasons. In the vast universe that surrounds us, mysteries are waiting to be uncovered. Among these are the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a strange twist. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for our understanding of how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. It tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments used to explain time dilation is the light clock. Imagine being inside a spaceship, moving at an incredible speed, close to the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel in a straight line, bouncing vertically. However, to an outside observer who is not moving with the spaceship, things look different. They see the spaceship moving at high speed and observe the light beam's path. Since the spaceship is moving, the light beam has to cover more distance to hit the mirror. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a longer diagonal path. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. This concept is not just theoretical. Experiments have confirmed these relativistic effects. For example, particles in particle accelerators like the Large Hadron Collider can reach speeds close to the speed of light. Scientists must consider the effects of time dilation to make accurate predictions and measurements. The special theory of relativity opens the door to a world where time is not a constant, where it can be stretched and compressed depending on your motion. It challenges our everyday intuition and leads us to the realization that the universe operates in ways far beyond our common experience. Einstein's special theory of relativity, introduced in 1905, reshaped our understanding of the universe's fabric, particularly in terms of time and motion. This theory reveals that the laws of physics apply uniformly for all non-accelerating observers, irrespective of their motion. This seemingly strange idea challenges our conventional notion of time. The concept of time dilation is one of the most fascinating and practical implications of the theory. Time can slow down or dilate depending on your motion. The faster you move, the slower time appears to pass for you relative to the stationary observer. This effect becomes more pronounced as you approach the speed of light. Imagine two identical twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their Earthbound sibling. This phenomenon, often referred to as the twin paradox, is a real consequence of time dilation. The reason behind this peculiar behavior lies in the invariant speed of light. As the space-traveling twin accelerates to high speed, the ticking of their clock appears normal to them. One of the most famous equations in physics, E equals mc squared, is a direct outcome of special relativity. This equation states that energy and mass are interchangeable, meaning that mass can be converted into energy and vice versa. This principle is fundamental in understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. The special theory of relativity forces us to reconsider our intuitive notions of time and space. It demonstrates that the universe operates in ways that defy everyday experience. Time is not an absolute concept but is relative, influenced by motion. The constancy of the speed of light and the relationship between energy and mass are central ideas confirmed by numerous experiments. Now, let's delve into the general theory of relativity, another groundbreaking concept put forward by Albert Einstein in 1915. This theory takes us into the realm of gravity, revealing a profound connection between gravity and the very fabric of the universe. At its core, the general theory of relativity challenges the classical concept of gravity as a force that acts between masses. Instead, it presents gravity as a consequence of the curvature of spacetime. To understand general relativity, we need to think of the universe as a four-dimensional entity, combining three dimensions of space and one of time. In this four-dimensional spacetime, massive objects such as stars, planets, and even you cause the fabric of spacetime to curve around. Imagine spacetime as a vast, flexible fabric. Gravity. A massive object like the Earth creates a dimple in this fabric. When you place a smaller object like a ball near the Earth, it rolls towards the dimple. This is analogous to what happens when an object falls under the influence of gravity. It's not a mysterious force, but is simply following the curvature of spacetime. General relativity provides a powerful explanation for the motion of celestial bodies in our solar system. It correctly predicts the orbits of planets, such as the elliptical path followed by Earth around the Sun. The old idea of gravity as an active force didn't fully account for these orbital motions, but the concept of curved spacetime does. One of the most striking confirmations of general relativity came during the solar eclipse of 1919 when Sir Arthur Eddington led an expedition to observe the bending of starlight by the sun's gravity. According to the theory, the sun's massive presence would curve the path of light from distant stars, making them appear slightly out of position. The observations matched Einstein's predictions, solidifying the theory's validity. Just as motion affects time in special relativity, gravity also has an impact on time. In regions of strong gravity, time passes more slowly than in regions of weaker gravity. This means that if you were standing near a massive object like a black hole, your clock would run slower than one located far from such a massive object. General relativity also has profound implications for the structure of the universe as a whole. Einstein initially added a cosmological constant to his equations to maintain a static universe. However, when it was discovered that the universe was expanding, he referred to this as his greatest blunder. The theory of an expanding universe, as supported by general relativity, forms the basis for the Big Bang theory, which describes the origin of the cosmos. Another significant prediction of general relativity was the existence of gravitational waves, ripples in the fabric of spacetime itself, generated by massive accelerating objects such as merging black holes or neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of gravitational waves, confirming yet another aspect of Einstein's theory. Over the years, Numerous experiments and observations have tested general relativity, and it has consistently withstood scrutiny. Whether it's the precise orbits of planets, the bending of starlight, or the observation of gravitational waves, the theory has repeatedly been confirmed. Some scientists propose that there might be additional yet undiscovered factors or forces at play that could replace or augment our current understanding of gravity. These scientists explore various possibilities, including theories that introduce new particles or interactions. It's essential to note that alternative theories are not dismissed out of hand. The scientific community rigorously tests these ideas to determine their validity. In Einstein's theory, we've got four-dimensional space, and then you're prevented from traveling back in time by the speed of light. It fits into the geometry in that way, although you can imagine wormholes and ideas that involve tunneling through and taking shortcuts. It's important to highlight that skepticism and dissent are integral to the scientific method. In the pursuit of knowledge, it's healthy to question established theories and explore alternatives. Through skepticism and exploration, science progresses. When scientific consensus is questioned, it can lead to further investigation and a deeper understanding of the universe.